Hello Internet world, welcome back to the wonderful world of math where the sun is always shining and the math is always exciting. Today is lesson 10 in unit 1 of calculus. So this is really the crux of calculus. This is not just one of the main points, I would say it is probably the main point of calculus, and everything revolves around the idea that is presented today. Okay, today we're going to talk about the difference between a secant line and a tangent line and how to determine the equations of those lines. Now, that might seem very minimal in terms of all the scope of mathematics, but there are so many applications to the idea of a tangent line, what you can do with it, replete throughout a lot of different applications in life. And from here on out, the rest of calculus is built upon this idea, how to expand on it, how to simplify it, how to make it work quicker for us, and then how to apply it. So I'm really excited about this particular lesson and this idea moving forward, okay? And so you can see in the objective that the idea of the secant lines and tangent lines helps us understand the idea of speed or of rate. And we'll get into that as well as we move along here. First thing we need to understand is the idea of the average rate of change. Now, maybe in a prior math course, you have been exposed to this idea, the average rate of change. Another way of saying that is just the average slope between 2 points. And in Algebra 1 or in Math 1, you learn how to write the equation of a line. But then later on, you learned about other functions that aren't linear, but we can still connect 2 points. We can always connect 2 points with a line, so it always goes back to the idea of a line. So the average rate of change is just the amount of change divided by the length of the interval. So it's the change in y over the change in x. It's just the slope. That's all it is. It's the slope of a line between 2 points. So here's an application of this, okay? In this application, I have the x-axis representing days, so t is now my x-axis, time, and then my y-axis is, we call it p. I don't know why I called it p, because it represents the number of flies, okay? So we have number of days, number of flies. Now we can apply this. The context could be how many flies are in a jar, or how many flies are on an island, or whatever it might be. How many flies have been killed by a trap, or whatever it is, right? So whatever the context is, the question is, what is the average rate of change over the interval? And we can see in this case that as time goes on, right, as time marches on, the number of flies is increasing. Okay, so maybe there are more and more flies in our jar, or there are more and more flies that are being killed day over day, right? So the question is, what is the average rate of change over the interval 23 to 45? So I'm going to go back to our trusty old slope formula. We know that the average rate, another way of saying average rate, is just the slope. So we would say y2 minus y1 over x2 minus x1. But because we are in higher level mathematics, we're not going to be just using y's and x's, because y is an equation, whereas we might have a specific function that we're focusing on, right? And so maybe we call f of x, right? But in this case, we call the function p. So we would write this as p of x2 minus p of x1 over x2 minus x1. So this is the y value at x2, and this is the y value at x1. Now we have these coordinates of 23, 150, 23, 150, and what's the other one? The other one is 45, 340, 45, 340. And so we just plug those in. We know how to do that. That's 340 minus 150 over 45 minus 23. And so that becomes 190, I believe, over, what is that, 22. 190 over 22. And that's, so we found the slope. Now let's talk about the context a little bit here. Okay, so the change in P over the change in T, the change in the number of flies over the change in time. Okay, so with that said, Calculating that out, like I said before, we're just finding the slope. That's easy enough. We get 190 over 22, and then that does simplify to 8.6. Now, I will add to this the units. The units here are very important. We have something on top and something on the bottom. What does the 190 represent? The 190 represents how many flies were added to our system, whatever it is. Because we ended with more flies than we started with, we added 190, right? So it's a positive 190. We added 190 over 22 days. So we would say that our units here are flies per day. Flies on top, days on the bottom. It's a fraction, just like this is a fraction. Flies over days is a fraction, flies per day. Now, what does that mean graphically? It means that if we draw a secant line that passes through those 2 points, all we're really doing is finding the slope of that secant line. And so when we say average rate of change, it just means to find the slope of a secant line. And if you remember back to geometry or math 2, the secant line is a line that passes through a curve at 2 points. Now, it could pass through more than 2 points, but we're only focusing on those 2 points. So back from geometry, we really only focused on a circle. A secant line passes through a circle at 2 points. Whereas a tangent line, oops, not the best drawing here, or at least not the best representation. The tangent line only skims the curve, skims the circle. It hits it only at 1 point. And so let's talk about the difference between those two things, okay? If I were to ask you to find the slope of that green line there, find the slope of that green line, well, I don't have much information there. I only have an x and an x2. Now we can extrapolate, we can call the y values what we want based on those x values. So we would say that the slope of the secant line is going to be f of x2 minus f of x minus x2 minus x. Now normally I know it's f of x2 minus f of x1 over x2 minus x1. But bear with me, I just got rid of the 1, and you'll see kind of where that comes from, or the reason why later on, okay? So instead of calling this x1, I'm just calling this x. All right, so finding the slope of the secant line is just finding the slope between those 2 points. Now what I'm going to do here, notice I put an h. I put an h that represents the distance from x to x2. How far is it from x to x2 we call h. And so my point that I'm trying to make is that I could say that the slope of a secant line, slope of a secant, can be written as f of x2 minus f of x over x2 minus x. That's okay. But what I want to try and accomplish is I want to try and write the equation of this slope in terms of only x. So I don't want any x2s in my equation. And so that's why I put the h there. Now we know this relationship. We can say that x2 is equal to x plus h. How do we know that? Because we know, let's say that the x value was 3, right? So this coordinate is 3 something. 3. And the h is 5. That tells me that the x2 is 5 units away from x. Well, if x is 3, then what's x2? It's going to be 8, because we take the 3 and we add the 5 to it. We add the h value. So we take where we start, we add some distance, and that's where we end. So our ending point is equal to our initial point plus some length, okay? So we're just defining it that way. Now that I have defined x2 in terms of x, I can now replace this x2 with this x plus h here. So another way to write the slope of the secant line would be f of, instead of x2, I'm going to put x plus h, minus f of x, because we want everything in terms of x, over, well, what's x2? x2 is x plus h, I'll put that in parentheses, and then minus x. So this is another way of saying the slope of a secant line. Now we might be able to reduce this. We can't do anything on the top there because this is f of a certain point and f of a different point. But on the bottom, we can see that we can simplify this to say f of x plus h minus f of x all over, well, the x and the minus x cancel out, and we're left with h. Remember, because it's the change in y over the change in x. Well, in this case, the change in x is h. So my change in y over my change in x. All right. So with that said, just recapping, we redefined x2 to be x plus h, the initial point plus a certain length. And then we just plug that value in to get a different expression for the slope of the secant line. Okay, and then we can simplify it there. So that's a way of expressing the slope of the secant line. Now, I want to shift gears and talk about the idea of a tangent line. So you can see what I just did here was I took my x2 and I'm going to move it closer to my x value. So I'm going to erase that x2 and I'm going to put another x2 in its place. Well, what happened? We move this line, or we move this x value over, so the h value got smaller, but look what happened. We're looking at a different secant line now, okay? Well, let's move it over a little bit more. Let's move that x2 value a little bit more over. Now we have a different secant line value. And maybe what you're noticing is, as we move the x2 closer and closer and closer to the x, then what this line starts to appear to be is a tangent line. Right? Now it's not exactly a tangent line because it is still between 2 points on that curve. But what's happening to the h value? The h value, as we move along, so I'm going to go back to this, as we move the h value along, we can see that the h, or as we move the x2 value closer to x, we can see that the h is getting smaller and smaller and smaller. If I wanted the equation for a tangent line, or the slope of a tangent line, how big would that h value be? Because a tangent line, let's say I've got a curve that looks like this. A tangent line is a line that will just skim off of that curve. So it's not like it's a line that cuts through the curve. It will never cut through it at a point. It will just skim off of it. So we would say that this, let's see, this could be a tangent line. This is the tangent line. Well, bad drawing. But this is the tangent line at that point because it just skims the curve at one point. Here, maybe we have another tangent line, right? It just skims the curve at that point. Now, if we're talking about, you can see then that if I extend this line further out, it will actually hit the curve at a second point. But we are saying that this line is tangent to the curve at this point, okay? This is not a tangent line because it's cutting through at that point. We want it to just skim off at that point, okay? So our goal is to figure out the equation for the slope of a tangent line. So what we do is we move the x2 closer and closer and closer, actually x2 closer and closer and closer to the x value, making the h value get smaller and smaller and smaller. Well, how small, in theory, do we want the h value to be? Well, we only want the curve, or we only want the line to hit the curve at exactly 1 point. So the 2 points that we're looking at to find the slope are actually, in a sense, the same points. We're taking 1 point and we have a second point that is 0 distance away from it, okay, in theory. So that would be the equation of the tangent line. So what we say is, let's make h 0. The problem is, if we make h 0, we have the slope of this line, h is 0, we get f of x minus f of x, because h is 0, over 0. So f of x minus f of x is 0. So we have 0 over 0, which is indeterminate. So if we could make h 0, then we could find the slope of the tangent line. We can't make h 0 because we have an indeterminate form of a fraction. And so that's where we get into the idea of limits. Remember, a limit is equal to the function's value, or equal to whatever we want, as long as the function is continuous, okay? And so we look at this idea of the tangent line here. The slope of the tangent line will be the same thing as this equation, except for we want the h value to be infinitely close to 0. So we're going to say the limit as h approaches 0 of what we call our difference quotient here, okay? So again, we could write it like this, where it's just x plus h minus x, but the bottom line is we're taking the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? This is the slope of the secant line because we're looking at two distinct points. This is the slope, what you see on the projector is the slope of the tangent line because we're looking at one point and a second point that's infinitely close to it. We're taking the limit as it gets closer and closer and closer to it. Okay? So let's go ahead and say that that h value is approaching 0. Then we would get something that is a tangent line. So just a side note, the slope of the secant line, another way of saying the slope of the secant line is the average rate of change, whereas the slope of the tangent line is the instantaneous rate of change, the instantaneous rate of change. In other words, how fast are you going at a moment, at this specific moment? And so let's go back to a previous lesson we talked about before. If I said, how fast were you going when you were driving to Disneyland? Well, that's going to change depending on the traffic and depending on certain moments in time. As you get on the freeway and as you get off the freeway, as you hit traffic, you're going to speed up and slow down, right? But the average rate of change is your total distance traveled divided by your total time that it took. That's your average rate. That is the slope of the secant line, okay? The instantaneous rate is what your speedometer says on your car, on your dashboard. That tells you how fast you're going at the specific moment. That is your instantaneous rate of change, also known as the slope of the tangent line, okay? Now, with that said, let's go ahead and take a look at an example of this. Okay? We are looking for the equation of the line tangent to the graph of f when x equals 4. So here we've got f of x is given as x squared minus 1, and we want the tangent line when x equals 4. That's our goal, is to create the equation of a line. And like I said before, we're going to be doing a lot of equations with lines, but what are the two things well, let me take a step back. Let's take a look at what this looks like graphically, okay? We have x squared minus 1, which means it shifted down 1. We'll follow our slope pattern just to get a good look at what the graph looks like, okay? And so here we have our parabola. Okay, there's our parabola. I identified a few points here. Now, we're looking for the tangent line when x equals 4, which is way out here. But let's just pretend that this is 4 right here. It's not, but let's pretend that it is. The question is, what is the equation of the line tangent to this curve when x equals 4? Well, if this is the position when x equals 4, then if I were to draw a tangent line here, I am asking for what the equation of that line is, okay? Now, what do we need in order to find the equation of a line? We need two things. We need a point and we need a slope. Those are the two things that we need in order to create the equation of a tangent line. Well, we know that the x value is 4, so it's pretty easy to find the point. All we have to do is plug 4 into that function. So we would say f of 4 is equal to 4 squared minus 1, which is 15. So the point is 4 comma 15. All right? That's what we're starting with. That is that point that we want to be tangent to the curve at. The next thing we need to do is to figure out the slope. Well, what did we just say? The slope of a tangent line is equal to the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x, if you would. Okay? So that's the equation of the tangent line. Well, what is the point that we're concerned with? We're concerned with the point of x equals 4. So when x equals 4, we're going to go ahead and plug that in. And so we end up with the limit as h approaches 0 of f of 4 plus h minus f of 4 all over 4 plus h minus 4. And so again, take a step back. This is just the slope formula. y2 minus y1 over x2 minus x1. The only difference is we rewrote our x2 in respect to our x1. So we have x1 of 4, and then we are moving over h units to get to our x2. But we are also saying that that h value should be infinitely small. It should be infinitely close to 0, the limit as h approaches 0. So if we can calculate this, then we can figure out the slope of the tangent line, okay? So now let's plug in and see what happens here. Well, let me do this off to the side. This might be helpful. How do I figure out what f of 4 plus h is? Well, I would plug that into that equation. So that would say 4 plus h squared minus 1, right? I just plugged in 4 plus h there. And then I can simplify that a little bit. That's going to be 16 plus 8h plus h squared minus 1. And then I can simplify that a little bit further. So that would be 15 plus 8h plus h squared. So that is my coordinate for f of 4 plus h. Then I need my other coordinate of f of 4. That one should be a little bit simpler. I'm just going to plug 4 in. That's going to be 4 squared minus 1, which we actually already did, which is 15. So we have our two coordinates. This is our y2. This is our y1. This is our x2. This is our x1. And then we just plug that in to this difference quotient here. So the limit as h approaches 0 of 15 plus 8h plus h squared minus 15, because f of 4 is 15, all over 4 plus h minus 4. Okay, so I'm going to go ahead and put parentheses around these things as I plug them in, because I think that one might be beneficial. And then we simplify this, right? Normally, because we're taking a limit, the first thing we would do is maybe plug in 0, but we'll still get indeterminate here. And so we can simplify this first, limit as h approaches 0. And we can see that this 15 minus 15 cancel out. So you're left with 8h plus h squared on top. And then the bottom is just h. Okay? And then here we can now factor. So this becomes the limit as h approaches 0 of h times 8 plus h all over h. And because we factored, we found that these reduce. You're left with 8 plus h. When I plug in 0 there, I get 8 out. Okay? And so this is the slope of our tangent line. So let me go ahead and summarize that for you. The point of tangent C was 4, 15. The slope of the tangent line was 8. So now let's go ahead and create the equation of the tangent line. It would be y minus 15 equals 8 times x minus 4. That is the equation of our tangent line. And it kind of makes sense because as we move further and further out here, closer to the actual value of x equals 4, we would see that that tangent line is getting steeper and steeper because the parabola is getting steeper and steeper. And so we would expect a pretty steep line with a slope of 8 there. Okay, so kind of to recap, to make sure everybody's in a good place with this, because this is throwing a lot out at you all at once. To find the slope of the tangent line, you do the slope formula, the y2 minus y1 over x2 minus x1, but we take the limit as h approaches 0, and because we know that the x value is 4, we'll just plug in 4, okay, and then evaluate each of those points and plug them in. Now what I did on the projector here is a good way of seeing it as well. You see, I identified f of 4 plus h separately somewhere else, and then I plugged it in into the difference quotient. I did the same thing with f of 4, and then I plugged that in. Here on the lesson, I just directly plugged in the 4 plus h into f of x here. So what is f of 4 plus h? Well, it's 4 plus h squared minus 1. What is f of 4? Well, it's 4 squared minus 1. But then from here we just simplify. We can see exactly what we have here, the 16 plus 8h plus h squared minus 1, and then the 15. And then we can simplify that, and it becomes 8h plus h squared over h. We factor out the h, so we end up with a limit as h approaches 0 of 8 plus h, which is 8. And then we can create our tangent line. So here's another graphical look at it. There is our tangent line. We can see it's pretty steep. We know that the point is 4 comma something, whatever that point of tangency is. So we plug that back in here, which we already did there. So that would be 16 minus 1, which is 15. Our coordinate is 4 comma 15. And then just plug that into the equation of a line, the point slope form. Like I've said before, not really interested in slope intercept form at all. There's only a couple cases in calculus where we want it in that form. If it's not specific, then just leave it in point slope form and you're fully okay with that. Okay, and it just makes for less errors as time goes on. All right, so here is an here's a practice problem that I want you guys to do. Go ahead and pause it and see what you can come up with. And then once you're stuck or once you think you have an answer, go ahead and unpause and see how you did. Okay, so this time we are looking for the equation of the tangent line of our function f of x, but in this case our function is 1 over x. And we are looking for the tangent line when x equals what? 2. When x equals 2. So remember, we need two things. We need a point and a slope. So the first thing we're going to do is find the point. That's the easiest part. The point is going to be whatever f of 2 is. So that's going to be 1 over 2. So our coordinate is 2 comma 1/2 for our point. Okay, no big deal. Now we need the slope. So the slope of the tangent line is equal to the limit as h approaches 0 of f of x plus h minus f of x all over, and I'll go ahead and do it, x plus h minus x. You could just put it all over h because that will always reduce to h. The x's will always cancel out. So we've got to figure out what these two values are. Well, first of all, we got to figure out what f of x plus h is when x is 2. So we're going to say the limit as h approaches 0 of f of 2 plus h minus f of 2 all over 2 plus h minus 2. Okay, so we have that. And from here, what is f of 2? Well, limit as h approaches 0. F of 2 plus h is going to be 1 over 2 plus h minus, what's f of 2? F of 2 is 1 over 2. So that's our numerator. And our denominator will just simplify. Well, I'm going to go ahead and write it out just so we can see it, so I can point to it. Okay. There's my y2. There's my y1. There's my x2. There's my x1. If you're having a hard time seeing it, then I would maybe go ahead and write it out over here. What is f of 2 plus h? Well, that's going to be 1 over 2 plus h, because I just plugged that in there. And what is f of 2? That's going to be 1 over 2. So there's my y2, my x2, my y1, my x1, and I just plug it into the slope formula. It's the slope formula. That's all it is. You just have to recognize it for what it is. Okay? Now from here, we might want to try substitution. If I plug in 0 for h, I get 1 over 2 minus 1 over 2, which is 0. If I plug in 0 here, I get 2 minus 2 is 0. It's indeterminate. So I have to do some sort of algebraic manipulation to make this work. And really, the problem lies in the numerator, because the denominator, get rid of all these parentheses here, the denominator just simplifies to h. So that's not really our problem. Our problem lies at the top. So how could I change that? How could I manipulate that algebraically in order to make it look different but produce basically the same thing? Well, I could get common denominators and somehow combine those two fractions, somehow subtract those. So what would be a common denominator? Well, I would have to multiply the first one by 2 over 2, right? And then the second one I'd have to multiply by 2 plus h over 2 plus h. That will give me a common denominator. And so let's go ahead and simplify this. This is going to be the limit as h approaches 0. And then if I multiply that by 2 over 2, I end up with 2 over, and I'll distribute the 2 in there, 4 plus 2h, minus, multiplying this, we get 2 plus h, over, distribute there, 4 plus 2h, and then that would all be over h. You go, well, that looks like it's more complicated than it was. And yeah, to a degree it is. But now I have a common denominator here. So let me go ahead and put that here. The limit as h approaches 0, this is going to end up being 2, well, I'll go a little bit higher here, 2 minus 2 plus h all over 4 plus 2h, and that's all over h. Okay, so we have a fraction divided by h. Okay, now I can simplify that top a little bit to be the limit as h approaches 0. 2 minus 2 is 0. We're going to distribute the negative, so that becomes negative h over 4 plus 2h, and then all over h. Okay, now how do I divide that? If you don't see it right away, you could write it out. We're dividing fractions, so it's negative h over 4 plus 2h divided by h. Well, we're going to put that over 1. And then, because we're dividing fractions, we're going to flip that, so it becomes negative h over 4 plus 2h, and then times 1 over h. Look at that. Those h's reduce. And so you're left with negative 1 over 4 plus 2h overall here, okay? So this simplifies. Basically, the h in the numerator here reduces with the h in the denominator there. I'm not looking for shortcuts. I'm looking for you to understand that. That's basic fractions, but you still need to understand it, so make sure you get that component. But the bottom line is that this simplifies to the limit as h approaches 0, okay, of negative 1 over 4 plus 2h. And now I can go ahead and plug in 0. If I plug in 0, I get negative 1 over 4 plus 2 times 0, and that simplifies to negative 1/4. And so that was my slope. And some of us are sweating because we just worked so hard to just find a slope. I get it. I know, that was a lot of work. Be patient with me. But this is my slope of my tangent line. Give me a second, I'm just going to double check this. Yeah, that's correct. Okay. See, I used a quick shortcut that I know based on calculus that I will teach you in the future. So that's something to look forward to, that you can do all this work in a matter of, I don't know, 3 seconds. But we have to learn where it comes from and what it means. Okay? So now that we know the slope is negative 1/4, slope is negative 1/4, we can create our tangent line. It'll be y minus 1/2 equals negative 1/4 times x minus 2. And that is the equation of our tangent line. All right, that was a lot of work, but be patient with it. You guys gotta make sure you understand it. You gotta make sure you get this. It's a very important concept, okay? So again, taking a step back, looking at this, we plug it into our difference quotient. We've got our y2 minus our y1 when x equals 2. And then the bottom already reduced to h. I just did that earlier on. And then we find a common denominator there. Okay, we find a common denominator. And then we simplify it. And we can see that the h on top and the h on the bottom will end up reducing. And then we can go ahead and plug in 0. And we end up with negative 1/4. And again, our point was 2 comma 1/2. Plugging that into our point slope form, we have our tangent line. Okay? And we can go ahead and check our work here, just to make sure, to verify this graphically, okay? I'm going to go ahead, no I don't. Okay, I'm going to go ahead and erase this and graph the function, okay? I have the information and I have my answer as a result of it, but let's go ahead and look at the graph to verify that this makes sense in our head. What does the graph of 1 over x look like? Well, it's the rational function, the normal rational function here, right? We are looking for the tangent line when x equals 2. So if I go over to x equals 2 and I plot that point and draw a tangent line, we can see that that tangent line has a y value that's positive there. Check, it does. And it has a negative slope. And in fact, it does. Now my graph is very rudimentary, so that may not be an exact negative 1/4. It may not be a height of 1/2, but at least it's in the right quadrant and at least it's heading the right direction, so I can have a little bit of confidence in that. So that's kind of cool that I can now create the equation of a tangent line, or another way of saying that is I can figure out how fast something is changing at a moment in time. Because normally we need 2 points to figure out slope. Normally we need 2 points to figure out a rate of change. But calculus, the main point of calculus, is to figure out how fast something is moving or how fast something is changing at a moment in time. Okay? So we got one more slide to go, and I'm going to add a new word in your vocabulary. Maybe you're familiar with it, but the word is normal. Oh, I'm very familiar with that word. My parents call me, they say I'm not normal all the time, right? No, I'm joking. Anyways, so a normal line is a line that's perpendicular to the tangent line. A normal line is perpendicular to a tangent line at the point of tangency. So if I look at a graph, let's say that this is my graph here. If I draw a tangent line at, let's say, this point, C, so if I'm looking for the tangent line there, that's the line that just skims off of the curve. The red line there is my tangent line. The normal line is the line that is perpendicular to this line. Now, wait a minute. You can draw an infinite set of perpendicular lines. You can have a perpendicular line here and here and here and here and here. The normal line is the line that is perpendicular to the tangent line at the point of tangency. So it's the one that hits the point of tangency of the tangent line. So there is only one normal line in comparison to a tangent line, okay? It has to hit the point of tangency. So the normal line and the tangent line are perpendicular at the point of tangency, okay? Let's go ahead and take a look at an example of this. And the work is going to look very similar to what we just did. But instead of wanting a tangent line, I want a normal line instead, okay? So let's go ahead and work this through. And you guys should be familiar with how to find the slope of a perpendicular line, which means you know how to find the slope of a normal line. So we know that f of x is equal to 3 minus x squared. Now, that's just written in a weird form. It could be negative x squared plus 3. That's fine. But we are looking for the normal line when x equals 2. That's the question. Well, again, we need two things. To find a line, the equation of a line, we need a point and a slope. So let's go ahead and find our point first. Our point is going to be f of 2, because that's our point of tangency, which is also our point of normalcy, I guess you could say. So that would be 3 minus 2 squared, which would be 3 minus 4, or negative 1. So our point is 2 comma negative 1. All right? That is the point of tangency. The next step is to figure out our slope. Well, our slope is going to be the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x. And again, I know that I keep writing this down. You can just put h, but I'm just trying to emphasize the point. That's y2, that's y1, that's x2, that's x1. Okay? We are looking for the point when x equals 2. So we're going to go ahead and plug in x equals 2. So that's going to be f of 2 plus h minus f of 2 all over 2 plus h minus 2. And our goal is to figure those things out. Well, what is f of 2 plus h? F of 2 plus h, again, if you need to write this out over here, hopefully you get to the point where you don't need to do that. F of 2 plus h means plug in 2 plus h to that. So that'll say 3 minus 2 plus h squared. Okay? And then we could simplify that to be 3 minus, we're going to put parentheses around this, 4 plus 4h plus h squared. And then simplify that further. That becomes 3 minus 4 minus 4h minus h squared. Simplify that further. That becomes negative 1 minus 4h minus h squared. Okay? So this is my f of 2 plus h. I'm going to plug that in. That's going to say negative 1 minus 4h minus h squared. And then we need f of 2. So f of 2 is going to be 3 minus 2 squared, which is 3 minus 4, or negative 1. Again, I already did that work up there. I don't need to redo it, but I did anyways. So that'd be negative 1 for f of 2. Notice I'm putting parentheses around everything so I don't mix up my signs. All over, and the bottom simplifies to h. But again, y2 minus y1 over x2 minus x1, again, it's just slope. Okay? So I'm going to go ahead and erase this just so I have enough room. And then I'm going to simplify this. The limit as h approaches 0, simplifying all that, that's negative 1 minus negative 1. Well, that's negative 1 plus 1 is 0. So we're left with negative 4h minus h squared. All over, those reduce, and you're left with h on the bottom. We can now factor out the h. So the limit as h approaches 0, factor out the h, you get negative 4 minus h, and then all over h. We can see that the h's reduce, and so we can say that our answer is going to be negative 4 minus 0, or negative 4. Now, what did we just find? We found the slope of the tangent line, right? This is the slope of the tangent line. So I'm going to go ahead and write that here. The slope of the tangent line, t, tangent line. So this, again, is the slope of the tangent line. We don't want the slope of the tangent line. We want the slope of the normal line. What does normal mean again? It means perpendicular. So how do we find the slope of a perpendicular line? We take our original slope and we do the opposite reciprocal. So if the slope of the tangent line is negative 4 or negative 4 over 1, then we would say the slope of the normal line or the perpendicular line is positive 1 over 4. Reciprocal and opposite. So the slope of the normal line is 1/4. Okay, so now we have everything we need. And we can write our equation of the normal line. We would say normal line is y plus 1 equals 1/4 times x minus 2. And that is my answer for the equation of the normal line at x equals 2. Okay? Now I can add to this without doing any more work. What is, not the slope of the normal line, the equation of the normal line. Okay? What is the equation of the tangent line? Normally you would have this done first because, sorry, that is the slope of the normal line. What am I doing here? That is the slope of the normal line. The normal line's equation is that. And so then we would say the tangent line is the same thing except our slope's different. So it would be y plus 1 equals negative 4 times x minus 2. Okay? But I was asking for the normal line in this case, so this is my answer. All right, I know that that was a new thing. It was kind of mind-blowing that you can find the slope at a singular point by taking a limit. Remember, the slope at a singular point basically is the slope of the tangent line, and then the normal line here is the perpendicular to the tangent line. But that's just a side note, really. The main focus is how to find the equation of a tangent line, and therefore how to find the instantaneous rate of change. You're going to want to commit this to memory, this equation. This is very important, right? But I also want you to understand where it comes from. Again, y2 minus y1 over x2 minus x1, and all we're doing is we're taking our points, our 2 points, and we're moving one closer and closer and closer and closer to the other one until the gap between them is essentially 0, and that's why we say h is approaching 0. With that said, that wraps up this lesson. If you have any questions, please reach out to me either through comment or email, but I will talk to you again later.